Alright, so at this point, I would like to discuss specifically redox reactions going on among oxygen-containing families of organic compounds. So that includes alcohols, carbonyl compounds, and carboxylic acids, and the derivatives. So ideally, you should be watching this after the discussion of alcohols and carbonyl compounds, but before carboxylic acids and the derivatives. So we start. So here we all start with an alcohol. With alcohols, I mean. So here we have a primary alcohol, obviously, because this is the alpha carbon and one of its groups is R, but only one R, so that's why it's primary. Here we have two R groups attached to the alpha, that's why we call this a secondary alcohol. And since in this we have three, we have a tertiary alcohol. Okay. Now, if we oxidize a primary alcohol, we should be able to get something we already discussed in alcohol, so that's why I wanted you to watch the video alcohols first. So what happens is that to make things even clear, I'm going to encircle all hydrogens that can be oxidized. So here, let's use one hydrogen. Then what happens? Instead of carbon bonding once to this oxygen, the carbon will now bond twice to the oxygen by virtue of this of spending up on this hydrogen, and then this untouched hydrogen will remain. So if you oxidize an alcohol, a primary alcohol, weakly, you produce an aldehyde. And again, the reagent for this oxidation is either PCC or periodinane. Now, if you oxidize this further, or if you go straight to oxidizing it strongly, so here we call this partial oxidation. But here we use strong oxidation. We use here strong oxidation using a strong oxidizing agent such as chromic acid, potassium chromate, or potassium dichromate. I think chromate also has a charge of positive 2. Anyway, I mean negative 2. So anyway, you have chromium containing compounds as strong oxidizing agents, and we're going to spend this remaining hydrogen to produce now a marker just flew. Alright, carboxylic acid. Now if you're going to reverse the process, you're going to have a reduction of some sort. You could either go for partial reduction. If you want a partial reduction of a carboxylic acid, you will produce an aldehyde. And you need a weak reducing agent, and usually we use this NaBH4. So this is named as sodium borohydride. This is weak, weak. So you use that to convert a carboxylic acid into an aldehyde, because anyway it is a partial reduction. But going further or going straight, you want a strong reduction. You use a strong reducing agent such as this LiAlH4 or lithium aluminum hydride. So again, this is strong. So whether you have a carboxylic acid or an aldehyde, if you subject it to lithium aluminum hydride, you will always end up with a primary alcohol. Now, when you have a secondary alcohol and you want to oxidize it, there's no partial or strong oxidation in secondary alcohols. Whether you oxidize it using PCC, periodinane, or chromium containing compounds, you will always come up with something that would use up this H, and that is ketone. Again, such as the same as in aldehydes, the first H will be used to form a double bond with oxygen. Same here, this single bond to OH has been converted to a double bond to O. So it's the same, right? Now you stop there. Why? Because you don't have any more hydrogens to oxidize. That's why you cannot oxidize this further. You cannot anymore oxidize this further. The only thing you could do with this is to reduce this. Doesn't matter if it's going to be a strong or a weak reducing agent. You just, whether you use lithium aluminum hydride or sodium borohydride, you will always come back from a ketone to you will always come back with a secondary alcohol. Now with a tertiary alcohol, you don't have any hydrogens to use anymore. So really, you cannot oxidize it anymore. So tertiary alcohols, just to clarify, are the alcohols which are not oxidizable, simply because you don't have any hydrogens that you could use for oxidation. So I hope that's clear, and I hope you would now move to the next topic, which is carboxylic acids.